Hello, everyone. So let me see here. 5 people in the chat. Um, well, I guess we can start. People who aren't here can always watch it later. I'm seeing that my audio levels are good. Let me know if I'm speaking into and you don't hear me. Today's or this week is the week of the test, and your test will be on Friday during this time period. And so, what we're going to do today is I'm just going to go over what's on the test and topic wise, and we'll do a few problems to fill in the time remaining. And Wednesday, unfortunately, I have some medical tests that I have to attend to, and there's no way around that. You have to operate on their schedule, not on our schedule, and so I won't be available. In the morning, I may be available at 2 o'clock. I don't know, but you know what? You guys, you can always catch me. I'll definitely be home in the evening, so you can always get on the Google Hangout, or just email me, and I can just create all right, maybe I'll email everyone and say, look, I'm available, and if there's enough people that want it, I'll just create a live stream, and we can go over things more. But I think you guys will know what's on it, and it'll be just more of a question of practicing stuff, which I'm happy to do. So, what are the topics on the test? They're here, and the first one is measurement and unit conversion. It's very simple. I don't want to really do a problem on that today because it's kind of trivial, unless you want me to. And if you want me to, just say something in the chat, and of course I'll respond to that. I look over at the chat every once in a while. I do see a question. Quick question, will these live streams be saved? So yes, the live streams are saved. They are all saved. And you know what? Maybe what I should do is just email you, everyone, the playlists, the YouTube playlists that have all the live streams. So yeah, they'll be saved. And that's actually the point of doing the live streams rather than doing Zoom. The annoying thing was that there was like this little bit of a lag, but the good thing is that they're automatically online, okay, on our channel. So the answer is yes. All right, so let me go back here, and let's go on. The first non-trivial thing we studied was general 1D kinematics. Okay, and in general 1D kinematics, we had, let me see here, I think I had something written somewhere else. No, I guess I don't. In general 1D kinematics, we have, I give you like the position as a function of time, and you can derive all kinematic quantities from it, and we'll do a problem on this. Okay, I don't have any equations there because it's very more conceptually driven than equation driven, but it's the idea that once you have the position as a function of time, you can derive the velocity as its first derivative, and then you can derive the acceleration as its first derivative. Okay, and then we looked at some specific examples of 1D kinematics under certain assumptions. One of them was constant acceleration, 1D kinematics. And they are the equations, the general equations, which are a little bit too abstract to apply in many situations. They reduce to these three equations here, okay? And so you had x. The first one is x is a function of time, describes where it is as a function of time. The second one is the velocity as a function of time. And the third one is really the other two with time eliminated. It's useful for solving problems, okay? And we'll do that one. We'll do one of those. I'd rather do some of the older ones together than the newer ones, because we just did the 2D stuff last week, so it's probably fresh in your mind. It's better to go back to the beginning and repeat some of those, and jump into the chat at any time and just say, hey, I'd like to see another one of these or whatever. Okay, and then we did another example of a oh wait, what's going on here? Oh, I think I have the wrong I'm looking at the wrong. Oh, all right, we had this technical problem earlier today. There we go. Okay, let me just see here. Yep. Okay, sorry about that. It was on the wrong window. Okay, so we did also a 1D harmonic oscillator. And this is, again, one-dimensional motion, but unlike constant acceleration, a good example of that is things that are falling, or a car which, steps on the gas and accelerates or slows down, but always in a straight line. A 1D harmonic oscillator is just anything that bounces back and forth like that. all right, doing sinusoidal motion back and forth like that along one dimension. And there are three equations for that. One of them is this omega, which is the angular frequency. It's not what you measure in the lab, but it appears in a lot of equations and even later in the course. Okay, that omega, the angular frequency, depends on the period, and the period is the time for one complete cycle. Okay, then there's a Vmax as the oscillator oscillates back and forth. Okay, it is actually has zero velocity at the end points, but it has a maximum velocity that passes through the middle, and that's given in terms of omega. And A, which is the amplitude, and the amplitude as the oscillator bounces back and forth, the amplitude is the maximum displacement, the furthest the oscillator gets from equilibrium. Okay, so that maximum displacement is called A, the amplitude. Omega, well, we just said what that was. If you multiply those two together, you get Vmax, and that's the velocity that occurs as it passes through equilibrium. At the endpoints, it stops, so the velocity is zero, and so the maximum velocity happens in the middle. And then there's the maximum acceleration, which is omega squared times A. There's an extra omega in there, and that occurs at the endpoints. Even though the velocity stops there, that's when the oscillator is being swung around the most. It's being accelerated the most at the endpoints. Okay, and so we get that A max is equal to omega squared A. And we'll do a problem with this as well. Okay. And then to prepare for 2D kinematics, we had to introduce vectors, and I showed you how to convert vectors. So the first two formulas here are converting vectors from polar to Cartesian, that is r and theta to x and y. Okay, let me put an extra space in there so you can see how they group together. Okay, so if I give you the magnitude of a vector and I give you the angle at which that vector is directed, you can get the x and y values by these equations here. Okay, I'm not going to do a problem with the conversions. The conversions were fine, and like I think almost everyone got perfect on that assignment, which I expected. You know, it should not be that difficult. Okay, and now, if I give you the Cartesian values, that's x and y, you can calculate r and theta using the square root formula here, or the Pythagorean theorem, which says that r is equal to the square root of x squared plus y squared. And also, you can get theta, the polar angle, from the inverse tangent of y over x, but because the inverse tangent is that multi-branched function, you have to worry about what quadrant you're in. So if you're in quadrant 1, you don't add any angle. If you're in quadrant 2 or 3, you add 180 degrees. And if you're in quadrant 4, you add 360. Okay, and so that's it for vectors. There was one other thing I didn't give you. I probably should have put a question on it in the assignment. It was kind of trivial. I dropped it because you don't need this, how to add vectors, until actually after the test. But I'm going to have a question on the test on how to add vectors. And so we'll do an example of that. It's really simple, and I think maybe it's good to keep all the vector stuff together. But it's really simple. Adding two Cartesian vectors, you just add all the x components, and that gives you the total x, and you add all the y components, and that gives you the total y. Okay. So we needed this new mathematics because 2D kinematics is based on vectors. That is, position, velocity, and acceleration are all vectors. Time is still a scalar, which just means a single number. Okay, and so we did constant acceleration in 2D. All right, and that was like the projectile motion, where you're firing something and it does that parabolic path. And we've done a lot of, well, I don't know if we did a lot, but we did some of those problems last week together. I gave you a few, and then this week's assignment is actually on this. So I don't think I want to do one of these problems. They take a lot of time, and you're still in the process of practicing them. But again, if you want me to do one, you want to just see one, I can easily create these like during a Google Hangout or whatever. Okay. Or maybe an extemporaneous live stream later in the day after I'm done with all those medical tests. Okay, and then there was uniform circular motion, and in uniform circular motion, it's basically an object traveling around a circle with a constant velocity. It's not speeding up or slowing down, and these formulas basically relate the tangential velocity to the period. Again, there's also a period of the motion because it's going in a circle, so it takes a certain amount of time. Starts at a point in the cycle. How long does it take before it gets back to that same point in the cycle? That's the period, capital T. And so 2 pi r over capital T, that gives you the tangential velocity. 4 pi squared r over t squared, that gives you the acceleration. And if you eliminate the period between the two, you get this formula: A is equal to V squared over R. Okay, and that's yet another formula that you can use to solve problems. I'm also not going to do one of these. They're pretty simple, and again, it was last week, and so you've got one on you've got one of these on your assignment that's due this week. Okay, let me take a look in the if there's any questions. All right, I don't see any questions in the chat there. A question that I was asked this morning, and I know this question is always coming, is like how many questions are on the test? And I'm still debating on a couple of them. I spend a lot of time thinking about what questions I want to ask and which ones I don't. It's going to be more than 24, but less than 30. Okay, and you should be able to do this in an hour, no problem. Okay, I'm going to give you 2 hours. That is from when you start the test to when you complete it. You get a complete 2 hours, and that's really overkill. But I do that because I'm just worried that if you have some technical problem, I really can't help you at my end, and you might spend 5-10 minutes trying to get past this technical problem. I don't know what it might be, so it hasn't happened in the past, but who knows? And so I don't want you to start freaking out if you have that, because it happens, especially if the technical problem happens at the beginning of the test, you start to get panicky and stuff like that. So just to relieve some of the stress, I know that the test, or I anticipate that the test should take you an hour, because I time these things, and I figure if it takes me 15 minutes to work through it, it'll take you an hour. Okay, so I usually multiply by a factor of 4, and so I pretend that I'm drawing out the pictures and all that, and I just say, well, how long did this take me? And if it's about 15 minutes, 20 at the utmost, then I think you can do it in the hour. If it takes me longer than that, then I've asked too many questions, and I've followed this rule for many years. It seems to work. Okay, so that's what's on the test, those 7 topics. Okay, and hopefully I didn't go too fast for you guys to write it down, but you can always look at this later. And let's start off. Let's start off with doing some problems here. So number 1 here, the measurement and unit conversions. I'm not going to do that because I'll do that just embedded in the other problems. Okay, and you can see that I was actually on the wrong page, because you see here this general 1D, I do have the formulas here. Okay, and for general 1D, you have the average velocity, which is like a delta x over delta t. You take some finite interval that it's traveled, divided by a finite amount of time, and that gives you an average. But if you shrink that interval down to an infinitesimal, it turns into a derivative, and so you get that v is the derivative of x, and a is the derivative of v with respect to time. Okay, so here's a problem. Let me just cut and paste it. I'm going to cut and paste the solution too, but we'll go through it. We'll go through it slowly. And I lost the image. Yeah, I know this happens sometimes. I'll get it in just a second. This is getting actually quite annoying, but yeah, a bit of patience here. I'm not sure why it's happening a lot today, but it is. So let's see. Is this the one? That is. Okay, there we go. Okay, let's take a look here. So I just cut and paste a bunch of stuff in there, but I'll go over it slowly. So take a look here. I give you that equation there. Okay, so basically that is x is a function of t. That's not x times t, but x is a function of t. So what is the position as a function of time? And you can see the stuff on the right hand side is all time, and that'll give you the position. Okay, and then I ask you to find the position, the velocity, and the acceleration at t equals 1 and t equals 2. I say etc. because you could do this at actually an infinity of times, but why? I mean, it's kind of silly. If you could do it at a couple of times, you could do it at all other times. And I also ask what is the average velocity between t equals 1 and t equals 2 seconds. So average velocities, because they're a finite interval, you can't just say what is the average velocity at an instant in time. You have to say what's the average velocity over some interval of time. Whereas the instantaneous velocity, you can say what's the instantaneous velocity at t equals 1 second, what's the instantaneous velocity at t equals 2 seconds, and so on. Okay, so at t equals 1 second, well, x is the position, so there's nothing to do there. You just plug in 1. So here we had t 3 times t cubed minus 5t plus 7. So wherever you see a t, you just put in a 1. So you got 3 times 1 cubed minus 5 times 1 plus 7. Okay, I'm sure you guys know how to do this. And then that just reduces to 3 minus 5 plus 7, which is 5. Okay, so where is this thing at t equals 1? It's at 5. I assume I'm working in MKS meters here. I didn't say what the units were, but it's not that important. Okay, and then where is it at t equals 2 seconds? T, you just put in t equals 2 there, so it's 3 times where that t is, you put a 2, so now it's 2 cubed, which is 8. 8 times 3 is 24, and then minus 5 times t, so that's 5 times 2, which is 10, and then plus 7, okay, and that turns out to be 21. Okay, great. Now you know where it is at t equals 1, and you know where it is at t equals 2 seconds. The next question gets a little harder because I ask you, what's the velocity at those times? Well, I don't directly give you the velocity information, but that's where you make use of this. Okay, and what's that? Well, that states that the velocity is the first derivative of the acceleration. Sorry, the velocity is the first derivative of the position with respect to time. Okay, and so that's this stuff right in here. Whoops, right in there. Okay, whoops, to there. Okay, so so I just rewrote v is equal to dx by dt, and you have to know how to differentiate. All right, so let's go through it. The 3 here, oh, I better scroll down just a little bit. There we go. Okay, the 3, so we're differentiating x here, that function x up here. Okay, the 3, it just goes along for the ride. Let me just highlight where the answer is. Okay, so the 3 there just goes along for the ride. There's the 3 right there. Okay, the t cubed, when you differentiate it, the exponent comes out front and becomes 3, and then the t cubed, the exponent decreases by 1 and becomes t squared. So the derivative of t cubed is just 3t squared. Okay, so where is it here? This piece right here, when you differentiate it, it just becomes that piece right in there. Okay. Then there is the minus 5t. Notice I skipped a t squared, okay? But that's okay. You've got other examples of that. That was actually your assignment, had a t squared in there. So you have minus 5t. The derivative of t with respect to t is just 1, okay? So that'll just give you minus 5 back. And then the 7, which is a constant, the derivative of 7 with respect to time, a constant has no doesn't change over time, so its contribution to the derivative of 0. Okay, so you can see that the 7 disappeared there. So the derivative of 3t cubed minus 5t plus 7 is 9t squared minus 5. Okay, that is the velocity as a function of time. Okay, and now what? Well, I didn't ask for that in general. I could have, but I didn't. I said, what is the velocity at t equals 1? Well, you take the function here, 9t squared minus 5, and then for t, when you're 1, you just put a 1 in there, and then the rest is trivial. Okay, you've got 9 times 1 squared minus 5. 9 times 5 is 4. Okay, so the velocity at t equals 1 second would be 4 meters per second, presumably. Okay, and then what about at t equals 2? Well, 9 times, now it's not 1, but 2 squared minus 5. Okay, so 2 squared is 4 times 9, 36, minus 5 is 31. Okay, and so there you go. There's the velocity at those 2 points. Okay, and then finally, the acceleration. How do you get that? Well, the acceleration, let me scroll down a little bit more. That's this part in here. Okay, the acceleration is just the derivative of the velocity with respect to time. Okay, and the velocity function we had up here, 9t squared, that t squared, when you differentiate it, becomes 2t. Okay, so we got 9 times 2t, and then the minus 5, just like the 7 disappeared, the derivative of a constant is 0. Well, the derivative of negative 5 is 0, so it disappears. And so the acceleration just reduces to 18 times t. Okay, 18 times t. So, of course, at 1, it's just 18 times 1, which is 18. And at 2 seconds, it's going to be 36, okay, meters per second squared, presumably. All right, so there you go. There's the position, velocity, and the acceleration obtained purely from the position function at t equals 1 and t equals 2 seconds. Okay, let me take a look if there's any questions in the chat here. Whoops, I clicked on the wrong thing and I lost. All right. There we go. Okay. Sorry, I clicked on the wrong thing, and of course, everything broke. Okay, I don't see any questions in the chat there. Well, let me continue. All right, and But you should see the screen again. I apologize for this technical glitch. Um, I'm not exactly sure what triggers it, but okay, I know how to get around it. Okay, so the other question was about average velocity. I said, what's the average velocity between t equals 1 and 2 seconds? And for that, you have to use this formula here. So there's the last part of it right there. The average velocity is you take delta x. Okay, and I can't do the v with a line on top, so I just wrote average v there like that. But you take the whole distance that's traveled during that 1 to 2 second interval, and you divide it by the time between 1 and 2 seconds, which is obviously 1. Okay, and so the delta x there, you say, well, how do I get that? Well, it's basically going to be your where you are at t equals 2 seconds minus where you are at t equals 1 second. Okay, so there's your delta x. It's like, where am I after 2 seconds? Where am I after 1 second? The difference between the two is how far I traveled. And from above, you could just look up those numbers. It was 21 minus 5. So you traveled 60 meters between 1 second and 2 seconds. So that's your delta x. That's how far you travel. The time from 1 to 2 seconds is obviously 1 second. 2 minus 1 is 1. Okay, and so if you divide the two, you're going to get 16 like that. Okay. And well, there it is. Okay, so this kind of completes the kinds of questions I could ask for this problem. Okay, again, let me look in the chat here. Is everyone good with that? All right, if everyone's good with that, let's go on. So whoops, wrong window again. I seem to be clicking all over the place today. Okay, so here we are. This is constant acceleration in 1D. Okay, and the equations are, I went over them briefly, but let me just repeat them. X is equal to 1/2 a squared. A is the acceleration times t squared, so 1/2 at squared, plus v naught. That's your initial velocity. Your velocity at v equals your velocity at t equals 0. So v naught to t plus x naught, and that's x naught is your initial position or where you are at t equals 0. Okay, and that's one of them. The other one is your velocity after time t is equal to at plus v naught. Again, a is the acceleration, t is the amount of time that evolved from the initial, and then v naught there is your initial velocity. And then the last one eliminates time between the two. You get v squared is equal to v naught squared plus 2a x minus x naught. X minus x naught is how far you traveled. Okay, and so let me just cut and paste a problem that I have here. And along with the solution. Okay. All right, let me see if that's working. It is, okay. Well, we should draw the picture. You almost can get away with not drawing the picture here, but I kind of want to be careful. So let me switch to another screen and we'll draw a quick picture and do this problem. I guess I should read it first, okay. So car is driving at 65 kilometers per hour and speeds up to 100 kilometers per hour over a distance of 100 meters, okay. And I want to know the acceleration and the time. Okay, so starts at 65, speeds up to 100. All right, and also notice that we'll have to do a conversion because kilometers per hour, you need it in meters per second. All right, so quick picture here. And first draw the picture the way you would see it. Physically, what would you see? Here's the road. Here's the car. See, technically, you would be drawing a movie, but you can't draw a movie, right? So I'm going to draw the car 2 points in time, like that. It's dynamical, so like it changes over time, but you can't draw the change. You could just, it's a static picture. So here the on the left there's the car at initially, and on the right there's the car after some time. And I don't know how to draw the acceleration, but you know, I'll just draw an arrow here. It's just speeding up like that. Okay, that's a terrible A. There we go. That's a better A. Okay, and so that's the first part. The second thing you need to do is put a coordinate system. In other words, a ruler, and also a point in time when you start your t equals 0. So the ruler, you know, we're just going to run a ruler, the x plus x-axis along the ground here. Okay. All right. And where is the car initially? Well, that's x naught. Okay. And, you know, the ruler, you can put the 0 of the ruler anywhere you like. So why don't we put the 0 of the ruler when the car just starts to speed up? And so, so x naught is going to be 0 meters. Okay. And if that sounds arbitrary to you, just think about it. Like if you're measuring something, you can put the zero of the ruler wherever you want. At some point, the car was, like the car was traveling at 65 and then steps on the gas, speeds up. At the point where they start to speed up, that's x equals 0. Okay, that's where I'm going to put the zero of the ruler. And then they finally get up to 100 kilometers per hour. That I'm just going to call x. And that happens after 100 meters. So that position is 100 meters there, like that. The initial velocity is here. Okay, and I said that was 65 kilometers per hour. And it speeds up over here to 100 kilometers per hour. So I agree that this is a pretty trivial diagram compared to like the 2D one, but you might, like just not to make a mistake, not skip the step. There's only one other thing to say. This is the t equals 0 frame right over here. So this is where the car is at t equals 0. And this later time, I don't know. I don't know. All right. So now we've got everything we need. We have initial position, initial velocity, final velocity, time, and acceleration. We don't know the time, we don't know the acceleration. Let's switch back. Okay. And let's start here. So the first thing is I did give you the initial and final velocity, but I gave them to you in, there are in metric units, but they're not MKS. They're not, distance is measured in meters. We want mass measured in kilograms and time in seconds. Okay, we haven't used mass yet. We will right after the test. Okay, so kilograms, you just need to know that. Okay, it's not grams, it's kilograms for mass. Okay, but meters and seconds. Okay, for distance and time. Well, I've got kilometers and hours there, and that's not meters and seconds. This conversion happens so often, you could almost memorize what to do. Just divide by 3.6. Just take that 65 and divide by 3.6, and that's the answer in meters per second. Now, you might say, how do you know that? And the answer is that you could do it the way I showed you to do the conversions with those conversion fractions. But it's kind of trivial. To go from kilometers to meters, multiply by 1,000. To go from hours to seconds, divide by 3,600. So if you multiply by 1,000 and then you divide by 3,600, that's the same as just divided by 3.6. Okay, so it's something that you tend to memorize pretty easily. All right. I do have other conversion questions on the test that are not quite as trivial, so just bear in mind. But you will have to do this kind of a quick conversion, so you might as well use the shorthand. 100 kilometers per hour, that turns out to be 27.8 meters per second. So great, you've got the initial and the final velocities. Okay. You also have the initial and final position. I didn't write that in here, but I probably should. I should probably write it up here. X naught is 0 meters, and X is 100 meters, like that. Okay, so there you go. That came directly out of the diagram. All right, now you have to decide which equation to use, and you see it there, but how did I decide that? How do you know which equation to use? Well, if you look at the equations here, you notice that I didn't give you time. In fact, you could probably down here as another set, you could say A is equal to question mark, I don't know, and T is equal to question mark, like that. And there's all the quantities of interest in 1D kinematics, okay, constant A. And you see the time is a question mark. And so if you go and look at these guys, these equations here, the first one won't work because you don't have T, okay, and that'll mess that one up, okay. And you don't have T and you don't have A, so you want to solve for A, and how can you solve for A if you don't have T in that one? The second one, same thing. Actually, the second one, same thing. A and T, you don't have. The third one works, okay, and the third one doesn't have time, but it has A, and so you can solve for A in that one. Okay, great. So here we are. I just rewrote the equation there. Okay, and for V, we're going to substitute 27.8 squared. For V naught, 18.1 squared, plus 2A is the unknown, X minus X naught, it's the total distance, and that is 100 meters. Okay, so just 27.8 squared, there's 771, and there's the 18.1 squared. 2 times 100 is 200, and then there's an A there. Rearrange, divide by 200, and you get that A is equal to 2.22 meters per second. Okay, whenever you get an answer, always ask this question: is it a reasonable answer? Okay, and I'm not I'm always trying to do numbers that, like, I make up the numbers, but I'm thinking to myself, what's a reasonable number here? Like look at what I said in the problem. Okay, you're traveling at 65 kilometers per hour, and you speed up to 100 kilometers per hour. Well, I mean, you may not know kilometers per hour because, in the US we use miles per hour, but if you drive on the other side of the border, or if you just convert here using Google, 65 kilometers per hour is around 40. Okay, and 100 kilometers per hour is like 55 miles an hour. So you're speeding up from about 40 miles an hour to 55 miles an hour, and in 100 meters. And 100 meters is about 300 feet. Okay, and so you think to yourself, okay, that's kind of it's not too much of an acceleration. I mean, you'll feel it. I mean, you are speeding up, and 300 feet. It doesn't sound like it sounds like a lot when you're walking it, but it's not that far when you're driving. You'll pass that distance in no time at all. In fact, we'll see how fast you can travel 100 meters. In a second. And so, this is a reasonable set of numbers here. And so we get this acceleration of 22 meters per second, like that. And you say, well, what can I compare it to? And there's an acceleration which everyone experiences all the time. It's the acceleration due to gravity. Now, in the test, we'll round it off to 10 meters per second squared, but it's close to 9.8 meters per second squared. And you're going to measure it in one of your labs. Okay, I don't know if you've done that already, but I know that it should be soon. I think it's lab number 4. But anyhow, so this is 2 meters per second squared compared to 10, about a fifth of a g. That's about right. That's about right. A fifth of a g or a quarter of a g. I mean, if you had like a full g of acceleration, it's like you'd be pulled back into your chair as by your own weight, by as much as your own weight. I mean, gravity's pulling you down with your weight, but then you'd be pushed back into your chair with the same weight. And that's not going to happen unless you're in a jet or something like that. Okay, so cars can't, well, ordinary cars can't accelerate that fast. Okay, so yeah, that sounds reasonable. Okay, so always do that. And I'll tell you right now, like on the test, I've got some really unreasonable numbers. So that immediately eliminates a couple of the possibilities, and it narrows it down. So there you go. Okay, and then the second question was, how long does it take? And now you could use either equation 1 or 2, but why use 1? You might as well just use 2. It's the easier of the two. And you're trying to solve for t, and now you know a, and you could solve for t, and it turns out to be 4.37 seconds. Okay, so let me see here if there are any questions. All right, I mean, it looks like everyone's happy here. I agree that once you've done 2D, and like 2D projectile motion requires a lot of steps. Okay, once you go back to the 1D, you wonder what's so difficult about this, and that that's true. It really is pretty. These really are pretty straightforward problems. Okay, so all right, let's move on. The harmonic oscillator. Okay, gave you a description of it before, and it's something that bounces back and forth. Okay, and the displacement from equilibrium goes as a cosine. Okay, and so there's this angular frequency omega in terms of the period, and then there's a Vmax and an Amax. Okay, and so here we go. Let me just cut and paste a question here. All right, paste. All right, let me see if I can squeeze everything in. There we go. Okay, so the question is, an oscillator is found to have a period of motion of 2.5 seconds. Okay, and the velocity is found to be 10 meters per second when it passes through equilibrium. All right, now the first question I ask is, what is the maximum velocity? And the answer is 10 meters per second. Now, I ask these kinds of questions because I want to make sure that you understand at which point in the cycle the maximum velocity occurs. Notice how I wrote the question. I said the velocity is found to be 10 meters per second when it passes through equilibrium. I expect you to know that that's also the maximum. The velocity at equilibrium is the maximum velocity. Okay? And so I could have asked the question, like, I don't have it here, but here's another question. What's the acceleration at equilibrium? And I expect you to know, if you go through your notes, expect you to know that the acceleration at equilibrium is 0. The maximum acceleration occurs where? The maximum acceleration occurs at the endpoints. Okay, so maximum velocity at equilibrium, maximum acceleration at the endpoints. Okay, 0 velocity at the endpoints, maximum acceleration at equilibrium. Okay, No, maximum acceleration. I don't think I said that right. Maximum acceleration at the endpoints, zero acceleration at equilibrium. Okay, so all right. So what is maximum velocity? Vmax is equal to 10 meters per second. Okay, and so nothing really except just you have to conceptually understand velocity at equilibrium is maximum velocity. What is the amplitude? Okay, and so you take a look at these equations here and you go, well, I need to solve for A. They're like that. And you don't know anything about Vmax, at least not yet, because I didn't ask you anything. You do know Vmax. You know Vmax. You know it's 10 meters per second here. Okay. And you want to find A, and you don't know omega. And you're not going to get it from the third one, but you take a look at the second one and you go, oh, omega is just directly related to the period. As soon as I give you the period, I've given you omega and vice versa. Okay. And so you go, okay, well, let me get omega first. So first we'll use that omega is equal to 2 pi t. Okay, and you substitute in here 2 times 3.14 divided by 2.5, which is the period. Okay, so I say that the period of motion. I can say this in different ways. Okay, so not to be tricky, but I do expect you to understand that like it's the time for one complete cycle. So here I've said that the period of the motion is that. I could have said it makes one complete cycle in 2.5 seconds, something like that. Okay, so there are different ways of saying the same thing. I expect you to recognize that that means that t is equal to 2.5 seconds. And so when you plug into 2 pi over t, you get that the the angular frequency is 3.77 hertz are the units, or per second. They're both totally equivalent. Hertz is just another way of writing per second. We'll start to see that more and more in the course. Later in the course, like when I have forces, they'll be newtons, but newtons are just kilogram meters per second squared. So when the units start to get more and more complicated, we just sort of collect them together and give them one name, okay? And so hertz is just another name for one over second, all right? And now you can use that Vmax is equal to omega times A, but you're not solving for Vmax, you're solving for A, so rearrange, divide both sides by omega. A is equal to Vmax divided by omega, 10 divided by 3.77, and you get the answer of 2.65. Okay? And then finally, what else can I ask? So there's, there's really period, A, Vmax, and Amax. That's really all the quantities there. So if you've gone through all the other ones, the only one that's left is A. And so I ask you, what is the maximum acceleration here? And the maximum acceleration is just A squared times A. And so omega is like 3.77 squared. We found that up above here. Where did we find it? Right here. And then A we found also 2.65, and that tells us that the acceleration is 37.7 meters per second squared. All right. Now compare that to G. That is bigger than G, right? It's like 4 times bigger than G, right? It's like roughly 40. But I mean, this is a pretty abstract problem. I can't think of any real any situation in the real world that this represents. So, yeah, like you can get pretty big accelerations in oscillators. Okay, I once calculated the oscillations of the little cilia in your ears, and it's even though they're tiny, the acceleration was bigger than I expected. I can't remember the number now, but all right. Any questions with that? I mean, there's different variations on this. I can, instead of giving you Vmax, I can give you Amax, or like in the assignment, that was probably the hardest. I can give you Vmax and Amax, and then expect you to find omega, okay? And then find T and then find A. All right, and that's probably the hardest, where you have to realize that, you can isolate omega out of uh, uh, by just dividing these two. If you take A max divided by B max, you get omega squared A divided by omega, and it leaves just one omega behind, allowing you to solve for omega. Then once you get that, you can find T, and then you can find all the other quantities, okay, like A. All right. So let's see, any questions there? All right, 5 people are still viewing, and got an okay. Okay, so that was it for 1D, because we did constant acceleration and we did an oscillator, and then we had to do the conversion. Okay, and like I said, I'm not going to do these ones. They really are simple. I mean, I guess the angle there is a little bit complicated, but I mean, I hope you guys you tell me if you in the chat if you want me to do one of these. Otherwise, I'm just going to do the adding vectors in Cartesian. Okay, because that's the one that, like I said, I probably should have asked you a sample question on the assignment. I didn't. It just at the time it didn't occur to me that maybe that would have been a good idea because I said, oh, you don't need that till later in the semester. But I think it's good to. I did present it as part of that lecture. So, how do you do that? Well, um, let's take a look here. So, whoa, cut and paste there. Copy, paste like this. All right. Okay, let me see here. Oh, it disappeared. Yep, 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 yep. Not surprising. All right. Okay, so what's the situation? So I've got, look at that line right there. So I've got two vectors, and they're in Cartesian. So I've got, I call them x1 and y1 and x2 and y2. Okay, the x component of the first vector, x1, is 5, and the y component of the first vector is 7. Okay, and I want to add that to the x to another vector whose and y components are -3 and 5. Okay, and the rule is really simple. To get the resultant x, which I'll just call x here, what you do is to get the resultant x is you just add up all the x components. Okay, so you have the x component from the first vector, which is 5, and you have the x component from the second vector, which is -3. You add them together, and you get 2, like that. Okay, and then for the resultant y component, you take the y component from the first vector and you add it to the y component from the second vector, and that'll give you 7 minus 5, and that'll give you 2. Okay, so I agree it's trivial, but like I said, I didn't have you do an assignment on this. It was in that lecture, but I kind of like to always repeat things a few times, like in assignments, and then like during reviews like this, so that you see these problems a few times and you know what to expect on the test. Okay, so that's how you add vectors. If you have any questions on that, go ahead and ask. Otherwise, like I said, I'm going to skip these two. And if you do want to see those, I recommend that you uh, be around on Wednesday afternoon, and you can always email me and say, like, can we just start a live stream, and I can do that. I've been on live streams up to 3 hours, okay, before tests. Last semester, I think we had a 3 hour live stream. Not that you have to be on it for 3 hours, but I said, what the heck, I'll just let it go over the two classes, and I just took a few breaks in between, and it worked out okay. But if you just want an extemporaneous live stream, but these ones are on constant acceleration 2D, and that's where you have to draw an x and y, and get the initial position as two numbers, the final position as two numbers, the initial velocity as two numbers, final velocity as two numbers, and plug into these equations. Okay, now these equations here, I mean, you should memorize them. And I know it's open book, but the reason you should memorize them or semi-memorize them at the very least is so that during the test you're not putzing around trying to remember stuff. Okay, and what you might wind up doing is, like, even if you have them written down, you might confuse some of the variables or something like that. So having them memorized really helps you to focus in on which ones you want to use. Okay, now those three that I've highlighted there, they're really the same as the 1D ones. Okay, the names have changed because in 1D we used the variable x. There was only one dimension, and so we called it x. In 2D we called it x and y, but the acceleration was along the y, and so these three actually look very much like these three right here, wherever they are, right there. Okay, the difference being that x is replaced with y, and there isn't just one a, there's an ay and an ax, but the ax is 0, so that's ay, and the velocities, both initial and final, have x and y component associated with them. Okay, and so just if you memorize these, just replace x's with y's, and then put little component subscripts on all the other variables that need them, and then you can go from these equations to these equations here. Okay, So if we had been doing this in the classroom together, I would have expected you to memorize these. I don't like open book tests, but during in this sort of a situation, it just it's fair because I there's no way I can watch whether someone is uh, you know using notes or not. So I just thought I'd put everyone on a level field. Okay, so y is equal to 1 half ay t squared plus v naught yt plus y naught. Okay, and that's like the x equation above, and then vy is equal to ayt plus v naught y, and vy squared is equal to v naught y squared plus ay y minus y naught. Okay, and the uniform circular motion. I mean, it doesn't look like it right now, but it's actually very closely related to the equations for simple harmonic motion. And now the reason it doesn't look like it is because I introduced omega up here, okay, like that. And I did that, I mean, I didn't have to do it here. You could have just, like, instead of omega there, you could just put 2 pi over t and all of those equations. But later in the course, we're going to need omega, so I introduced it here. And I kind of wish, thinking about it now, that I could have just reintroduced omega right there. And I think I did for you guys the calculus, but I didn't for the other ones. But then you can see that there's an omega there. See v is equal to, see the 2 pi over capital T, that's omega. Okay, and so you get that v is equal to omega r. That's like your v is equal to omega a above. Okay, so it's actually the same equation. And then above you had a is equal to a max is equal to omega squared times capital A. That's like your a is equal to 4 pi squared r over t squared. The 4 pi squared r over t squared is your omega squared. And you go, what's going on there? Well, you see, when you have uniform circular motion like this, if you were to flatten that and just get the x projection, so it's kind of hard for me to do this with my hands. Let me just start to flatten the curve. Flatten it. There you go. So you see, start like this, and then just flatten it out. Flatten it out, like project it out. And it turns into simple harmonic motion. So uniform circular motion is a generalization, is a 2D generalization of simple harmonic motion. Okay, so there it is. And again, this is really simple, so I won't do one of these right now. Let me just, I've got about 5 minutes left here. Let me just give you some idea of how you should probably uh, study for the physics. The one thing you can't do, and hopefully you haven't done this because it might be too late, is binge watch all the lectures at the last minute, okay, and even the live streams at the last minute. It just doesn't work for lots of reasons. It takes your brain some time to assimilate this stuff. You really need the information, and then you need to do it as assignments, and then you need more information, then you need to do it, and then you come back and you look over the whole thing. You start to see bigger and bigger patterns in it, and that's the only way you can really learn physics. It's not like biology where you could just memorize a bunch of names, or I don't know, some pharmaceuticals where you memorize a bunch of medications. It's not really memorization, it's all procedural. So there's some memorization, but it's mostly procedural. So because it's procedural, you really have to do it. And the way you do it is by repeating the problems that you've seen. So I've given you problems during the pre-recorded lectures. You can reproduce them. You can redo them yourself. Watch what I did, and then you redo them. Try not to watch what I did. Try not to re-watch the question. Like, just write down the question, the initial question, because I always start my examples with the questions the way I would have worded them on a test or something. And then you just reproduce everything without watching what I did. If you can't, then go back and look at what I did. You can repeat my problems with slightly different numbers, okay? And that isn't quite as good, but at least I mean, it doesn't give you that much extra, but at least it gives you that one more time that you repeat the exact same procedure, okay? On the assignments, I also gave you questions, okay? And you can repeat those, all right? And the assignments also show you the format of the test. The format of the assignments, the format of the test is identical. And what else? And then like during the live streams, I gave you some extra problems, some ones that I did and some ones that I said that you guys do on your own. And like for the 2D one, I suggested, I think we did one where I was at ground level and you shot up to the top of a hill. I suggested being at the top of the hill and firing down, or being on level ground and just firing across, okay? And there's some possibilities there. So by repeating these, and each time you create a little bit of a variation, And it's good that you even yourself try to think of what those variations might be, because if you let me put it this way, when I started to get up into the upper years of my physics education, I was able to anticipate what the teacher was going to ask. Okay, I could say, yeah, I think there's going to be a question like that, and I think there's going to be a question like that. I was right more often than not, amazingly enough. And the reason is that I just started to see like what kind of variations were possible, and just the thinking out of all the different types of ways that I could ask the same, get at the same principles and re-ask these questions. That really that puts you one step ahead, and then it becomes trivial. To be very specific about what I mean, notice that in the oscillator problems, you've really got four things that you can play with: the period, A, Vmax, and Amax. Try picking any two and see if you can calculate the other two, okay? And that's it. Then that's the totality of all the possible questions that I could ask for the simple harmonic oscillator. All right, and so, well, there it is. Okay, so that's the end of the 50-minute class. Let me just take a quick peek in the chat here. We're down to 4, and that's okay. This is I wouldn't say it's an optional class, but hopefully people will watch this later that didn't watch it the first time. Okay, and unless there's any questions, we could just end the stream. So anyone have any questions? Are we all good? By the way, if you wonder why I do the thumbs up gestures and stuff like that, it's because I can see myself at the same time you're seeing me, and I can see how much lag there is. All right. Okay, so you've heard now. All right, I don't see any questions, so I think I'm going to end the chat. All right, bye-bye.